This is 18.3, and we're going to talk about the thyroid gland. We briefly talked about some functions of the thyroid gland previously, but we're really going to dive into its anatomy and its physiology in this video. So, the thyroid gland, this is one of the largest endocrine glands. It's extremely vascular, um, and it's heavily reliant on iodine to enter these follicular cells by a means of active transport, so an energy requiring uh, cellular movement. And it's the only gland that's actually going to store hormones. So when we look at it histologically or underneath the microscope, it's composed of many different follicles. And these follicular cells surrounding thyroglobin and thyroid hormones. We also have parafollicular cells, which you'll see between follicles. And I'm going to show an image on the next slide that will probably better visually represent um, that. So, in terms of physiology, follicular cells are going to secrete what's known as thyroglobin into the lumen of a follicle. Iodine and tyrosine are going to be necessary to produce T3 and T4. These hormones are going to be stored and attached to this thyroglobin that can then be absorbed into the follicular cells when the hormones detach from the thyroglobin, and then they can be released into circulation. So, parafollicular cells, these have the ability to secrete calcitonin. And calcitonin is extremely important because it helps us regulate uh, blood calcium levels. So, when blood calcium levels are elevated, we can secrete calcitonin. And what calcitonin does is it tones down the amount of calcium in the bloodstream. So, looking at the anatomy and the histology of a thyroid gland, so you can see here, let's look. So, thyroid located in the cervical region just below the laryngeal prominence that you can see here in the thyroid cartilage. It is a hourglass shaped structure, if you will, and it covers the anterior surface of the trachea, located just over top of the larynx here. And it's extremely vascular. You can see our superior thyroid artery. You actually have an inferior thyroid artery as well. And what you can see when we look at this histologically is that you can see the thyroid follicles, which are going to be full of the thyroglobin colloid that we just talked about, which is this pink blob here, if you will. And then surrounding that is going to be your follicular cells. And then in between those follicular cells, deeper that you can see over here, are your parafollicular cells. Now, thyroid hormones, those are going to be produced by those follicular cells. Those are what, if we go back to the image before, the follicular cells are the ones that are directly surrounding this colloid. And those are going to secrete your thyroid hormones, which we're going to refer to as triiodothyronine, which is T3, or tetraiodothyronine, or T4, also known as thyroxine. A lot of times in normal talk, a lot of people will inappropriately talk about T3 and T4 both as thyroxine. That's not necessarily the case, and we'll get into that a little bit. I'll probably accidentally do this in class, as will many of you. We usually associate T3 and T4 as the thyroid hormones that are circulating in the bloodstream, not necessarily 100% truthful. So, most is going to be transported in the blood bound to this thyroxine binding globulin that's produced from the liver. So, we'll refer to this as TBG. Um, Most of the time, or a little bit less than half the time, 40% of T4 is going to be converted into T3 in the cells. T3 is typically more potent, so T4 gives us a little bit less elevated or less potent version of thyroid hormone. So much of the circulating T4 is going to be eliminated from the body. Now, what happens in terms of how we're getting this into the cells? So it's going to be transported through the plasma membrane of the thyroid hormone transporters. It'll migrate to the nucleus and bind with the intracellular receptor molecules, and this can then initiate protein synthesis. Why do we care about T3 and T4? Because it has many effects on metabolism throughout the body in growth. So it can increase our basal metabolic rate. So this can increase the rate of glucose and the fat and the protein metabolism in tissues, thus increasing body temperature. It increases the activity of the sodium potassium pumps, which is also going to generate heat. It can also play a role in altering the quantity of and the activity of mitochondria, resulting in more ATP production, which is going to lead to more heat production. So you can imagine that if we had hypersecretion of T3 and T4, a person with hypersecretion or too much T3 and T4 would exhibit everything we just talked about, but in a greater quantity. So you would expect to see skinny running through ATP, breaking down nutrients and things for metabolism, also increased body temperature. T3 and T4 also play a role in regulating normal growth and the maturation of organs. This can be anything from teeth to the bones to the hair, connective tissues, the nervous tissue. And it also has regulation on many of the structural proteins of the plasma membrane. It does play a mild or permissive role for growth hormone. So I kind of just brought this up. And the reason I brought this up is that it's fairly common to come across someone you probably know has some form of hyposecretion or hypersecretion of thyroid hormone. We will refer to this as hypothyroidism if you have too low a thyroid hormone, or hyperthyroidism if you have too much. And it's important to be able to compare and contrast the differences between these two issues, because it really helps you understand the function of the thyroid hormones. So, someone who has hypothyroidism or too low of thyroid hormone, they're going to have a decreased metabolic rate, low body temperature, and they're going to have a cold intolerance. You'll typically see weight gain, reduced appetite in these individuals, reduced activity of sweat. Sebaceous glands will typically have dry hair, dry skin. Typically, we'll always say that their skin is cold, have a reduced heart rate. Blood pressure is usually on the lower end. Um, Heart will typically be enlarged, just not generating enough pressure with each contraction. Skeletal muscles typically not developed as well as possible, or not upkept as well as possible. They're typically sluggish. Muscles are weak. They look untoned. Don't really have the display that they should. It can also lead to constipation. Um, Myxedema, this is swelling of the face and the body, and this can be a result of subcutaneous mucoprotein deposits. Not necessarily super important for you guys, but we'll talk about myxedema in a clinical correlation in class. Apathy, can have coarse hair, rough, dry skin, decreased iodine uptake, and a possible goiter. I don't know if anyone's ever seen someone with a goiter before, but in the neck region, it'll look like an outgrowth or a swelling, and that is an enlargement of a thyroid gland. And that's occurred because of the loss of the negative feedback loop of the thyroid gland. If it just keeps producing hormone and storing hormone like the thyroid gland does, it'll increase in size and look like a mass on the neck. Now, with hyperthyroidism, these people will typically have an increased metabolic rate, higher body temperature, and a heat intolerance. They get hot really fast because they're producing so much body heat themselves. Weight loss is one because their metabolism's running so fast. Increased appetite because they're burning through so many calories and burning through all of their energy storage. Very sweaty. Typically, will have erythema or flushed skin. Skin will be warm to the touch. Typically, we'll find them a bit tachycardic, so rapid heart rate, elevated blood pressure. Uh, EKG or ECG will be abnormal. They may have um, different changes with their cardiac cycle and their EKG, which we'll kind of get into next chapter, and we'll kind of have a flashback to this. Can have weak skeletal muscles that are going to exhibit tremors. Most movements are going to be exaggerated. Reflexes are going to be exaggerated. They're going to have hyperreflexia. Bouts of diarrhea. Exophthalmos, this is the protruding of the eyes, and this is a result of the connective tissue proliferation behind the actual eyes themselves. So you have a huge deposit within the orbit of this excess connective tissue, and that will actually move the eyes anteriorly, and it'll give them this bulging or protruding look. These people are typically hyperactive. They have some form of insomnia. They're irritable. They can have short attention span, extremely restless, and that's because they're have such a high metabolic rate. They're just burning through all this energy, um, giving them all this extra energy to go and be restless, not be able to sleep, things like that. Typically have abnormally smooth hair, skin, and just overall kind of soft structures, increased iodine uptake, and these people almost always have a goiter. And in class, we're going to do a little activity where we're actually going to talk about why both hyperthyroidism and hypothyroidism will lead to a possible creation of a goiter. So when we're looking at the regulation of thyroid hormone, and we're talking about T3 and T4 secretion here, so like we had talked about before, stress, hypothermia, things of that nature are going to cause or thyrotropin releasing hormone, TRH, to release from the neurons within the hypothalamus. That's going to pass through the hypothalamo-hypophyseal portal system, and that's where it's going to get to the anterior pituitary that you can see here. So the thyroid or TRH is going to cause cells of the anterior pituitary to secrete TSH, the thyroid stimulating hormones, which are going to then be put out into circulation into the bloodstream, where they will then travel to the thyroid gland. So this increase in TSH is going to cause the synthesis and the release of T3 and T4 into general circulation of the body, so into the general bloodstream. Now that that T3 and T4 is in the bloodstream, it is then going to go act on all of its distant target tissues to produce some form of a response. With this negative feedback loop, though, concentrations of T3 and T4 within the bloodstream will also have an inhibitory effect on the secretion of the thyrotropin releasing hormone from the hypothalamus. So if you see on our image over here, you can see that we have TRH that's going to be secreted into the hypothalamo-hypophyseal portal system. That is then going to act on the anterior pituitary, which will then stimulate the release of thyrotropin releasing hormone to secrete this TSH. TSH will then be secreted out into general circulation to act on the thyroid gland. The thyroid gland will then ramp up its production of T3, T4 that will then be secreted into the bloodstream yet again. So T3 and T4 will go act on all those tissues that we just talked about to increase metabolism, increase body temperature, increase growth and normal developmental processes. But also, while in the bloodstream, it has the ability to act as its own inhibitor. So high concentrations of T3 and T4 within the bloodstream will act on the anterior pituitary, and it will inhibit it from releasing thyroid stimulating hormone, but it will also act on the hypothalamus to inhibit the hypothalamus from releasing TRH. Now that seems redundant, but majority of systems within the body are redundant because they have a backup plan. If one feedback loop or one organ or structure is no longer responding to a specific type of hormone, at least then you have another way to shut it off to help maintain homeostasis and regulation. And you'll see this collectively and continuously throughout all the other glands that we're going to talk about and many of the other systems in A&P. So we talked briefly about calcitonin earlier. We said that calcitonin is produced by parafollicular cells. Some people refer to them as C cells, but I'll typically refer to them as parafollicular cells. And they're secreted when there's high concentrations of calcium within the blood. And what calcitonin is trying to do is it's trying to decrease the amount of calcium concentration within the bloodstream. That's why it's calcitonin. It is toning down the amount of calcium within the bloodstream. Now, how do we tone down the amount of calcium within the bloodstream? A couple different ways that we can do that. Primary tissue that we're going to target is the bone itself. We need to decrease osteoclast activity. If you remember from AMP1, osteoclasts are the little miners that are in the bones, and they're breaking down the bone into calcium that will then go into the blood. So if we shut off the osteoclasts, they're no longer producing that free calcium that will go into the bloodstream. So that will decrease the amount of calcium within the bloodstream. It will lengthen the actual lifespan of an osteoblast. So the osteoblasts that are building bone, they're taking calcium from the bloodstream, depositing it in the bone. If we increase their lifespan and shut off osteoclasts, we should decrease the amount of calcium that is within the bloodstream. The other thing that we can do is we can inhibit the uptake of calcium um, from the digestive system, and we can also excrete it um, via uh, digestive system or the urinary system. So, primary functions of calcitonin helps young children early on, infant stages to, I think it's 6 or 7, 7 or 8, somewhere in that realm, against hypercalcemia after a meal. So that's too much calcium after a meal. Children are naturally eat meals that are very high in calcium. So to combat this, calcitonin plays a role to try to decrease the amount of calcium within their bloodstream. Um, like I said earlier, we can stimulate calcium to be secreted by the kidneys to remove it from the body. Um, we can also inhibit the action of parathyroid hormone. We haven't got to parathyroid hormone yet, but what it's going to do is it's going to break down bone um, when calcium levels are low in the blood to increase those levels. So we can talk about a couple different abnormal thyroid conditions. We're going to go over a lot of these in class, so I'm just going to briefly bring them up here in this lecture. I would read through the descriptions of each, have a general idea. But like I said, we're going to do an activity in class to go over these. So you can, different types of hypothyroidism and hyperthyroidism. So with hypothyroidism, you can have iodine deficiency. Um, you can have goitrogenic or goiter-causing substances, neonatal hypothyroidism, pituitary insufficiencies. Hashimoto's disease is probably the big one, and I will actually get into this a little bit. This is an autoimmune disease in which thyroid secretion is out of whack. It can be real depressed levels of thyroid hormone secretion. Also, just make it inactive. We'll go over this in class. This is a fairly common autoimmune disorder. And then you can just have a complete lack of a thyroid gland, destruction for various reasons, whether you had cancer or something or a tumor and you need the thyroid gland removed. You could have an abnormality where you just weren't born with a functioning thyroid. So many different things can cause hypothyroidism. And then hyperthyroidism, Graves' disease, we're going to get into Graves' disease a lot. Tumors, we can have different tumors that are benign, or it can be an adenoma, and this can cause an excess secretion of thyroid hormone, thyroiditis, so an infection of the thyroid itself, whether this is viral or less likely, but a bacterial infection. You can have elevated TSH levels. This can be a cause of an anterior pituitary tumor. So if you have a pituitary adenoma, anterior pituitary adenoma could cause hypersecretion of thyroid hormone. And then you can have thyroid storm. This is actually really fascinating. Like I said, we'll talk about these in class, but it's when you have the sudden release of T3, T4, and this is caused or as a result of a really stressful stimuli. So whether this is like really bad infection, it can be idiopathic, which means that we don't really know its origin. It can be caused by stress. It can be caused by surgery. And you have a huge release of T3, T4 into the body. And I'll actually show you some videos in class about this. So interactions between Graves' disease and other body systems. This is what I'm going to make as a self-study portion of this chapter, is I really want you to have a good understanding of Graves' disease and some of the other, and how it affects some of the other body systems. Again, we're going to go over Graves' disease in class.